Welcome to qnawire.
Hi there. So here we want to find what is the energy of the H2 plus cation with a nuclear interseparation equal to R. So the way to do this, essentially what we have is a system with two protons or hydrogen atoms and a single electron in which we have two different distances. One is R1 and the other one is going to be R2. In this case, in order to find the result, our answer is going to depend on the basis function that we're going to apply. In this case, our basis function, we're going to consider a superposition between one S functions of hydrogen atoms. Each of them is going to be centered at the corresponding nuclei. Let's say this is going to be hydrogen 1 and this is going to be the hydrogen 2. I'm going to put it in parentheses instead just to avoid any confusion. So my trial wave function is going to be a function that depends on R equal to a normalization constant times the linear combination of trial wave functions located on each of the nuclei. So my initial wave function as a function, my initial trial function is going to be equal to the solution for the hydrogen atom, 1 over square root of pi, a0 to the 3 halves, times the exponential of minus r over a naught, where a naught is the usual Bohr distance. Now, in order to find which is going to be the normalization constant, what we need to do is consider the overlap in between our trial wave function. Coming from this, the result that we're going to get is that this integral is going to be equal to, employing only direct notation just to avoid any results or any weird stuff. Sorry about that. Is going to be the a squared times the overlap of phi 0 at R1 times phi 0 at R1 plus phi 0 at R2, phi 0 corresponding for R2, my second function, plus minus 2 times the overlap in between both of these functions, phi 0 at R1 times phi 0 at R2. Since the wave function needs to be normalized, this integration needs to be equal to 1. Thus, the value for A is going to be equal to 1 over the square root of the result, which we're going to call, since these wave functions are normalized, this is equal to 1, this one is also equal to 1, and we're going to call this term the overlap, which is going to be S, just to keep the traditional result. So this would become 1 over the square root of 2 times 1 plus minus j. Sorry, 2 times 1 plus minus S over here. Okay? Now, the next part is how to calculate this value S. This S is going to be equal to doing the integration over phi 0 R1 times phi 0 R2 over the whole space. In this case, we can do this in in standard spherical coordinates. I'm going to I'm going to give you directly what is the result for this. And this overlap is equal to E to the minus X, which I'm going to define in an instant, times 1 plus X plus X cubed over 3. Where X is going to be equal to the ratio in between the radius R divided by the value for A0. This x is the one that is going to give us the energy as a function of the distance. So now that we have accomplished finding this result, let's go back to the Schrodinger equation and try to solve our final answer. Now what we're going to use is Schrodinger equation to find the expectation value of the energy. In this case, we need to take the bracket of the Hamiltonian operator that needs to be equal to the energy times the overlap of my wave function. Thus, the final result for the energy that we're going to find, or the expectation value of the Hamiltonian, is going to depend on our results for each of the hydrogen atoms. So what we wish to evaluate at the end is going to be 8 times this value. So, before we continue, let's state which is going to be our Hamiltonian operator for the electron. The Hamiltonian is going to be equal to minus h bar squared over 2 times mass of the electron, nabla squared minus e squared over 4 pi epsilon naught times 1 over r1 minus the potential corresponding to the second nuclei, 4 pi epsilon naught times 1 over r2. So, the interesting part is that since we're employing wave functions that are corresponding to the ground state of the hydrogen atom, our result is going to be in function of the ground state energy for a normal hydrogen atom. Applying our Hamiltonian into our trial wave function, what we're going to get is that this is equal to 8 times my Hamiltonian operator, to mass of the electron, times Nabla squared, minus e squared over 4 pi epsilon naught times 1 over r1. I'm going to combine here both of the results, 1 over r2, applied to my linear combination, phi 0 r1 plus minus phi 0 at r2, employing this r2 distance. Now, applying the first wave function onto the Nabla operator plus this first part of the potential is going to give us the energy for the ground state of the hydrogen atom. And the same thing happens with R2. Now the only thing that is going to change are the results when you combine R1 with the potential of R2 and vice versa. Thus, what we're going to get from this is going to be the ground state energy times my wave function minus 8 times E squared over 4 pi epsilon naught of phi 0 corresponding to R1 divided by R2 plus minus phi 0 of R2 divided by R1. And now this result we can write it down in terms of two different quantities, which we're going to call D and J. Let's call now to get the expectation value, which is this result over here, the expectation value of H. What we're going to get is that this is equal to E0 plus 4 times A squared times, we're going to call the first term D, plus minus, let's call the second one J, times the value for E0. How do we get this? Well, the value for D is going to be equal to the integral of phi 0 located at R1 times A0 over R2 times phi 0 at R1. And the value for J is going to be the one with the cross result. This is going to be R1 times A0 over R2, over R1 by 0, R2. Here we're not going to go through the integrals. This can be done directly using Mathematica or any other software, for example, Wolfram Alpha or stuff like that. But the final result, which we're going to write in terms of our constant x is going to be d equal to 1 over x multiplied by 1 minus 1 plus x times e to the minus 2x. And the value for j is going to be equal to 1 plus x multiplied by e minus x. Recall that from our definition, the value for x was r divided by a0. And with this, we can finally write down which is going to be our final energy in terms of these results. The final energy for our Hamiltonian is going to be 1 plus 2 times the value for d plus minus the value for j divided by 1 plus minus the value for s, which is the overlap. All of this multiplied by E0, which is the hydrogen atom energy. And with that, it would be all. This is our final result. Oh, sorry, actually, this is not the final result. This is only the electronic energy. Sorry about that. The total energy is going to be equal to this value for H plus the potential, which is E squared over 4 pi epsilon 0 divided by the internuclear distance, which is the potential, the nuclear potential. Recalling that this value is equal to the result can be related to the energy of the hydrogen atom, since the value for E naught is equal to minus E squared over 8 pi epsilon 0 A0. This total energy becomes our expectation value for H minus 2 over x, just to have everything consistent, times E0. And with that, it would be all. Thank you very much and have a good one.